Hola amigos! Today I bring you a new Unreal Engine tutorial where I will be showing you how to make this cool effect using Niagara. In short, we will be using color and depth information from a render target to recreate a scene as seen from the camera, using trigonometry to figure out where to place our system particles. Since we are working from a camera projection and not 3D space, in some way this is similar to how infrared depth sensing devices work, and can be used to produce similar images. This technique is quite flexible and can be used to achieve many different results. Stay tuned till the end of the video to see another cool variation of this effect. And now, without further ado, let's start the tutorial and see how it's done. I have a very simple setup here to demonstrate the effect, with a character and a camera framed onto their face. This character also has a looping talk animation to have more movement to show on the particle system in runtime. The first thing we need is a texture to save our camera image to. On the Create Asset context menu, select Render Target, found on the Texture subgroup. Give it a name, and for now just save it. We'll come back to its settings in a moment. Next, the camera actor needs a Scene Capture Component 2D, with its target set to the texture that we just created. Here, I have the simplest camera setup ever, but you could also use this effect to project an image captured from a moving object in your game, like some sort of a scanning drone, for example. With the render target set, we can go back to the texture and increase the resolution in the settings. For this example, I'll use 2048 by 2048, but feel free to adjust this number to the needs of your project. You can also use a different aspect ratio, but you will need to adjust your math later to stretch the UVs accordingly. I think I want this to look like some kind of personal comms device image, so I'm going to change the FOV of the capture camera to 30 to close in on this character's face. After this, I'm going to change the scene to have a nighttime lighting, but that's not part of the tutorial, so I'll just skip it. With all the scene setup done, we can finally create our Niagara system and start working on the effect. This time, we're gonna save some time by using a fountain emitter as a template. Please refer to my previous Niagara tutorial if you want to know how to create a system from scratch. On the dialog, select New System from selected emitters, add a fountain emitter, and press Finish. After naming and saving the file, we can open the Niagara editor, where the first thing we'll need to do is get rid of most of the modules. Select and delete the following ones: Gravity Force, Drag, Add Velocity, and Shape Location. Once you do that, you should end up with a bunch of particles spawning in a single point. Next, on the Particle Update stage, add a Sample Texture module. This will add also some compilation errors, because this module is not compatible with CPU particles. To fix this, we simply have to change the system to be a GPU sim, which can be done from the Emitter Properties panel. Let's look at the texture sample module's parameters now. The first one is pretty straightforward. We just need to plug in the render target texture that we created. However, we also need to assign each particle some UV coordinates, so it samples the texture at that location. We only have to do that once per particle, so add a set new or existing parameter directly to the particle spawn stage. We'll need a vector 2D, which I'm going to rename UV. For this example, I'll assign a random float in the 0 to 1 range, but you can experiment using sequential spawning or other methods to give each particle a UV coordinate. Back in the texture sample module, we can drag this new property from the property list to the UV parameter. However, nothing changes yet, because we are sampling the texture but not doing anything with that color information. Before we do that though, let's see how we can preview this UV coordinate property to better understand what we're doing. In the particle update stage, add another set parameter and add particle's position to it. We could create a scratch pad for this, but in this case we're going to set this value directly using an HLSL expression. Don't worry though, this one will be very simple. We're going to place each particle in a vector 3D whose x and y coordinates are going to be their UV property, then scale it and keep z as 0. The final code is float3 parentheses particles.uv times 500, 0. This will place the particles in a square 500 units long according to their position in the texture. Now we're ready to display the render from our camera in the scene. We'll use the scale color module that is already in the stack, but since we need the information from the sample texture, we have to move this one above the scale color. You can simply drag and drop the modules to reorder them in the list. Back in the sample color parameters, disable scale alpha and expand the list to show the color value to a scale property. Next, change this last value to the sample color output of the sample texture module. Cool, now we have a single blue pale dot. This looks weird, but it means it's working. If we go back to the scene, we can see why. This dot is the directional light behind the character, and we don't see anything else because the render target's alpha value is set to inverse opacity by default. A fun thing about the scene capture component is that you can use the alpha channel to store other information. On the capture source property, select scene color in RGB, scene depth in alpha. The issue seems to be fixed now, but let's drag a copy of the system to the scene so we can better see it in action. So far, this looks pretty good. The next step is to reproject the particles to the proper depth and do it from the emitter's location. If you remember, in our current code, we are placing the particles in absolute world locations, 0 to 500 units in both x and y axes. Doing this involves a bunch of trigonometry and math, but thankfully Unreal Engine has a function that does exactly that, so I'll spare you the pain. Back in the Niagara editor, in the particle update stage, look for and add this module. Recreate camera projection. This one has many parameters, but most of them are very straightforward. Let's take a look at them. The Write to Intrinsic Values checkbox means that the result of this calculation will be used as the particle's position. We can leave that on, so we don't need to keep the module that we have below. We will use it later though, so we just disable it for now. For FOV, we just need to match the value from our capture component, which I earlier set to 30. The projection space UV location is the UV property from our particles, so we can drag and drop it from the list on the bottom left. Next, for the transform vectors, we can use the system's X, Y, and Z axis. This way, we can control the angle of the system by rotating the emitter. And finally, we can get the depth from the alpha channel in our texture. To do that, set the value to a float from linear color and change the linear color to the sample color and set the channel to A or alpha. It seems like it's working, but let's go back to the scene to see it better. Now we have something that resembles our goal. This is a good moment to go back to the sprite and material settings and tweak them until you have something that you like. For this example, I think that I will just reduce the sprite size and increase the spawn rate by a lot. This is already a nice looking effect, but we can certainly do better. Before that though, you might have noticed that when I select the emitter, there are a ton of particles in the background that are not visible but still there. Let's see how to remove them. You could think of reducing the maximum render distance in the scene capture component, but this wouldn't get rid of the particles. Instead, we're going to add a Kill Particles module to the update stage and use it to remove those that are too far away. In this module, set the condition to bool by float comparison, and for the A value, we'll use the alpha channel of the sample texture, just like we did in the camera projection module earlier. For B, something like 700 or 1000 removes most of the stranded particles in this example. Perfect. All that background noise is now removed. One thing that you might want to change is the scale of the effect. Maybe you want to make a big projection on the side of a building or something like that. If you've been following so far, you might have noticed that after doing the camera projection, the effect is at the same distance and scale that the actual camera in the scene. A problem with scaling this is that since this is a perspective projection from a camera point, any change in scale is also going to change the distance from the emitter, making it harder to position in the scene. And there are multiple ways around this problem that involve some geometry and math, but I'll keep things a bit simpler for this video and show you an easy but usable solution. Note that even if you don't have to change the scale of the effect for your needs, we're also going to add a way to offset the particles, which will be useful later on. And we could do this writing another expression, but doing it in one line would probably be a bit confusing, so we'll create a scratch pad instead. In the node graph, add the particles position to both the get and set maps, and a vector input parameter to the get one. This parameter will control the scale, so I name it just that. One thing to note is that these particles can be anywhere in the world, so we need to convert their position to local space, do the scaling, and then transform back to world space. For that, add two transform position nodes and connect them to both get and set maps. Set the first one to transform world to local and the second one local to world. Simply adding a multiply node and scaling the position will work, but this will generate a number of warnings in the Niagara output log. This occurs because it is not safe to multiply positions and vectors, especially on games that use large-scale maps. Even if it doesn't affect this example, fixing it doesn't cost anything, so we might just do it. We just need to add position to vector and vector to position nodes before and after the multiply operation. Once these connections are replaced, all the warnings are gone. Back in the system overview, if we go to our scratchpad settings, we can set the scale parameter to use the system scale, which we can easily change from the editor viewport. Increasing the scale now reveals the problem with scaling a projection in this way, which is that the distance from the emitter is also increased. The solution is to add a second vector parameter to the scratchpad and add it to the position just before the multiplication. This method requires some manual tweaking on the offset and could get messy if you need to update the scale in runtime, but for most situations is perfectly valid. Once this is done and the system is saved and recompiled, we can move, scale and rotate the emitter in the viewport and tweak the projection offset in the Niagara editor. Now, since the beginning of this tutorial, we've been spawning the particles at the local origin, and then moving them instantly to the projected position for the remainder of their lifetime. But nothing stops us from moving them at a slower pace, so we can see each individual particle as it flies towards its final position. We'll have to make some changes to do so. First, disable the Write to Intrinsic Values checkbox from the camera projection module. I'm also going to add a shape location and use a small sphere to represent some kind of futuristic or holographic projector. Next, move the disabled Set Position parameter to the bottom of the stack and open the Scale and Offset scratchpad that we created earlier. We'll make the following changes. First, remove the particle's position from the Get map and replace it with a new input position. I named this one RCP position. We'll plug the value later. The other change that we have to make is to write this in a separate particle property, not the actual position. Fortunately, Niagara is smart enough to create a new variable if we simply rename the one that we currently have in the map set. We can go back to the scene now to see our particles in their initial sphere location. If we want to see the end result, we can now activate the disabled Set Parameter module and update the expression to use the new particle variable from the scratchpad. And this doesn't work because I forgot to change the input variable that we added to the scratchpad. After fixing that small mistake, we're back in business. Just plug in the output value from the Recreate Camera Position module and it should work just as before. Great, but this is just particles in either A or B positions. To make them go from one place to the other, we're going to replace the expression where we're setting the position for a Smooth Lerp over Time Position module. In these properties, set the smooth value to particle's position and the target value to our projected position variable. This is an interesting effect, but there's clearly an issue here. These particles are dying too soon, basically as soon as they reach their destination. We can accelerate them by changing the convergence rate on the Lerp module from a constant to a float from curve, and then scale this curve up so the particles zip towards the target location very fast and reach it before the end of their lives. You can tweak this curve to achieve different results, like slowing down the particles at first, then speeding them up again before slowing them one more time, or use negative values to make the particles flow back, things like that. Yeah, this looks pretty cool now. You can even use the slow-mo command to slow down the game and follow each individual particle as it flies to form the image, which I think is a pretty neat effect. To close the tutorial, I'll just scratch the surface of all the incredible things that you can achieve with color, and make the particles start as a very saturated and bright blue color and slowly fade towards the correct color from the capture. I think this will give it a bit more of that classic sci-fi hologram look. I did this by going back to the Scale Color module and replacing the RGB scale for a curve, where I changed the blue channel to be very high at first before quickly go back to a 1.0 scale. For the rest of the channels, I kept them at the default 1.0 scale throughout the particle's lifetime. And with that, we're done with this tutorial. Some cool other uses for this type of effect could be to display a game map, or to show a snapshot of another location or a moment in time. You can also apply some fun post-process to the render target texture before sending it back to Niagara to add distortions or glitching, or use dynamics to make these images form from, I don't know, a swirl of dust or other sources. The possibilities are unlimited, and I cannot wait to hear about what you guys achieve with this. To close the video, let me show you a variation that I made after recording the tutorial, and I will quickly go over the changes that I made. I achieved this Minecraft-looking version of the effect by replacing the sprites for a mesh renderer, and then tweaking the position expression to round the locations every 5 units, which was the scale of the cubes. On this one, I'm also spawning all the particles at once in a burst, and keeping them alive forever, to have the particles just move with the animation. I found that this variation works pretty well to display maps, and it reminds me a bit of that pin table from the X-Men movies. That's all I have for you today. If you made it all the way to the end, thank you for watching this video. And if you like this content and want to support the channel, please consider subscribing, it really helps a lot. See you next time!